Hello, eights. Good morning. So I want to take what we learned about the Pythagorean theorem last time and extend it to talk about the distance formula this time. Obviously, distance formula implies we're going to be talking about the distance between things. The main point to remember today is that the distance formula is the same thing as the Pythagorean theorem, except it looks more complicated. So we'll see it in a little bit. But it is the same thing as the Pythagorean theorem, which means anytime you need the distance formula, you can use the Pythagorean theorem instead. And Pythagorean theorem is easier to remember. So just quick review, what does the Pythagorean theorem say? It says, given a right triangle with legs A and B, I should not use the Oxford comma, and hypotenuse C, we know this relationship will always be true. A squared plus B squared equals C squared. So, and we saw this last time with these squares, like the squares on the legs always add up to make that same square that's on the hypotenuse. And we saw some visual reasons why that has to be true. So let's first just look at an example. Suppose we need to find the distance between these 2 points. I forgot to erase these, but that's okay. What I would picture is the triangle that's pictured, or I could picture the triangle that goes out here. It really doesn't matter which one you picture. And then I would be looking for what are these distances, because I want to find the distance here between those 2 points. So I know overall, I'm going to come down to using A squared plus B squared equals C squared. So then the A and B have to be the legs. So I'm looking at this side and this side. Well, I can count those. That's 4 and 3. And so I would have 3 squared plus 4 squared, or 4 squared plus 3 squared, it doesn't matter, equals that distance that I don't know. I'll just keep it as C, so this side is C. Good. So then this is 9, 4 squared is 16, equals C squared, and that all equals 25. So to get C alone, I need to square root 25, and I get C has to be 5. It could also be -5. I don't remember if we've talked about this at all, but in this case, it's a distance, and distances cannot be negative. So that doesn't make any sense. In this case, our distance has to be 5, which is great. What you notice here is we wanted to find a distance, and we didn't use the distance formula at all. We used the Pythagorean theorem to find the distance between these. And it makes it really easy to picture. A Pythagorean theorem is about right triangles. So if you want any distance, you just have to picture the 2 sides that are perpendicular to each other, count out those distances, and then use your Pythagorean theorem. So let's do the exact same process in general. Obviously, in general, things get more complicated. So I'm going to go ahead and take a picture or look at a picture of what this looks like. So we have 2 points. They could be in any of the 4 quadrants. I have no idea where these 2 points are. I'll just say, well, I guess to make it simpler, because I can picture what I'm going to draw, I'm going to draw them both in the first quadrant. But the same thing will be true no matter where those 2 points are. So I'm going to make this point A, that's x1, y1, and this point B. This is x2, y2. Good. Again, I want to picture the horizontal and the vertical distance here that are perpendicular, because now I can apply the Pythagorean theorem in order to find this distance over here. So hypotenuse is blue, legs are red, and I need to find what these distances are. Well, it's nice that here I have that y coordinate. I know this is y1. Same way, this b coordinate over here has a y coordinate, so this has to be y2. So if I look back, I have these coordinates, y1 and y2. How did I get 4 here? Well, I looked across at 6, and I looked across at 2, and I did 6 minus 2. Or in general, it wouldn't have to be 6 minus 2, like I could have counted this out. But in this case, I can't count this out. I have to know that it's going to be the higher one minus the smaller one, which is y1 minus y2. So this side is y1 minus y2. Great. Then if I look at this side down here, well, I have similar things. This has an x coordinate, that's x 2. This has an x coordinate, that is x1. Here's what's strange though. On this side, we kind of feel like we want to put x2, because it's larger, minus x1. Here's the problem with that. All of this stuff started at A. When I looked at this distance, I went y1 minus y2. So I started at A, and then I went down to get to B, which means in my horizontal distance, I also need to start at A. And if I start at A, I'm starting at x1. So that means this thing is wrong because I need to start at x1 minus x2. What you notice there is that whatever this coordinate starts at, if that's y1, this coordinate has to start at x1. Like those have to match. So, okay, now I have side length here and side length here, and I'll keep this as the distance that we want to find. In general, we know a squared plus b squared equals c squared. Well, those legs a and b are the y1 minus y2, x1 minus x2 things. So I'm going to have to expand these things to say I'll have that a object squared plus that b object squared equals c is just the distance. So that part is easy, squared. For the other two, I have this y1 minus y2, and I have x1 minus x2. Okay, good. Last thing, I want to get this distance because that's our goal. We want to find the distance. So if I want to get distance alone, you notice like this stuff is super complicated, but all that's happening to distance is it's being squared, and that's it. So to get rid of a squared, all I have to do is square root the distance. So I would end up square rooting all of the stuff on this side. And then we end up with this statement, distance equals, come on, equals all of this stuff up here. So I have this huge, huge square root over the whole thing, and I'm going to have stuff squared plus stuff squared. And in our case, I can see this is y1 minus y2, x1 minus x2. Now, everything we've done here is the exact same as what we were doing back here. The only difference is I don't know the coordinates of 3, 6, and 6, 2. I just know in general the coordinates are x1, y1, x2, y2. And the nice thing about this formula is that we can just plug those x and y values into here and it will return that distance. So if we wrote a computer program to do this, in Python it's really easy, then you would just plug in what are your coordinates and this would return the distance between them. So the distance formula then has lots of statements. They're all 4 of the statements are here, and you can see the only difference is here we started with y2 minus y1, so I needed x2 minus x1. I have to start in the same place always. So that means if I start with y1 minus y2, I need x1 minus x2. Oh, and I forgot something super important. All of these should be squared. My fault. Some people want to cancel out the squared and the square root, but the fact that you have a plus in the middle means you cannot. You have to leave them as squared. Same thing here, I just have the x terms first, and noting that x2 could come first, but then y2 needs to come first, x1 could come first, but y1 needs to come first. So the order really doesn't matter much. It just matters that you know if you start at coordinate 1, you need to start at coordinate 1 in both of those parentheses. Other than that, it's the same. So now you should hopefully understand where the distance formula comes from. And here, I'll go ahead and use the distance formula, but then I'd like to go back and just note that you could use the Pythagorean theorem and it works out the same. So if we had an application of the distance formula, say you work for the Coast Guard. So the Coast Guard goes and rescues people, and this person is in a boat, they've radioed in, they have GPS, so we have coordinates. I know nautical coordinates look different than this, and that's fine, because this is a mathematics application. If you're into nautical stuff, then we can talk. I love nautical stuff too. So the Coast Guard is located in Robin Hood's Bay, and they want to get out to this boat to save it. Well, how far will they have to go? So how far will they have to go easily can be resolved by just knowing here we have an x and a y coordinate. Here we have an x and a y coordinate. It doesn't really matter which one's 1 and 2. So I'm going to go ahead and make this coordinate 1 and make this coordinate 2. And then we want the distances between those. Well, I just have to plug those things in here. So I end up with distance is square root, huge square root, of x1 minus x2. x1 is 2.5, x2 is 7.7. So 2.5 minus 7.7 squared plus y1 minus y2. Well, y1 is 4.6 and y2 is 2.5. So I have 4.6 minus 2.5. And so then now all I have to do to find that distance is just simplify this stuff, and that's it. So our distance is then 2.5 minus 7.7 is 5.2, and negative 5.2 squared plus 4.6 minus 2.5, 4, 3, 2.1 squared. Great. Then I just have to go ahead and square these things, and I'm a little bit lazy right now, so let's just do negative 5.2 squared. Or I could do this, just so you know, this works. Squared, I get, was it 27.04? And this is written wrong, actually. I want this to be negative 5.2 quantity squared, which means it's going to return a positive, because negative times negative is positive 27.04. So here I have 27.04 plus square root is big equals distance 2.1 squared. Well, come on, 2.1 is 4.41, reasonable, 4.41. So then I just need 27.04 plus 4.41, that's 31.45, 31.45. Square root those things, and again, I'll say square root of, was it 31.45, I think? I'll just round it to 5.6. Was it 31.45? Good. It's about equal to 5.6. We don't have any units in this case. I'll just say units. Considering the application, these probably, whatever this coordinate system is, it's probably in nautical miles. So this is probably 5.6 nautical miles. That would be the most normal unit for that application. But good, you can see we can use the distance formula to do this. As a quick note, I'd like to just point out, come on, we also could use Pythagorean theorem. So Pythagorean theorem would say I need a distance here and a distance here. And to find this distance, I would just do that 4.6 minus 2.5, and I would get the distance there. Then I would do this 7.7 minus 2.5, and I would get that distance there. If you notice, the way I stated that, both of those turn out positive. And it actually turns out not to be a problem in this case. I should have squared here. It turns out not to be a problem because we square these things. If you noticed before, when we squared, everything turned positive. So like that negative number squared is positive, positive number squared was positive. So anytime we square things, they become positive. So it really kind of fixes things for us. And then we'd plug our stuff in and finish. I don't feel like I need to do that, and I don't want to waste your time. So this is really where I wanted to finish. Your guys' assignment for today looks like this, and there are some applications. So I wanted to note, first, you're just finding distance, so practicing. I don't care if you use the distance formula or the Pythagorean theorem. You have to be familiar with both. So I don't know. This is an application that's interesting. Computer scientists use physical problems in interesting ways, and they're very, very good at applying things. So this is giving an application of the Pythagorean theorem as a distance formula in computer programming, talking about transmitting files. And so I'd never heard of this application before. It's fascinating, and I'm sure that it's real. Video games they use vectors to see how things are moving, and vectors are always Pythagorean theorem. So this is obviously a good connection to distance. We have some archaeology work here, and then we have a ship that's doing stuff. Great. And this is like it's an interesting problem, but not an applied problem. So my final question when you finish all 6 is going to be, of all of these, I would say all of them are authentic applications, except for one. And I think when you work through them, you'll realize like, oh, this isn't the way these people do this. But the other applications I think are authentic. So I just want to know at the end, of the 4 applications here, which application is not authentic? Like it's not the way people actually solve those problems. That's all I got. Good luck, and I will talk to you soon, Nates.